All right, thanks very much. Just before I start, I'd like to follow on from a little bit of what Barry was talking about and say that I know most of you people here today view your red mud as a rather nasty sort of waste material that you'd rather kind of disappeared. I should point out that I don't see it that way. I see it as a resource. And in fact, when you look at the possible applications for it, I don't think we have enough red mud in the world to satisfy the environmental needs. And I mention this because I think it's very important. If we refer to something as a waste, we immediately start thinking of what nasty things it can do and how we can confine it and how we have to manage it and how much it's all going to cost us. But if we turn around and make a very simple psychological jump and we call it a resource, we now start to think, what are its properties and what can we use it for? And I think that's the stage we're at now. So let's start off with this. And in a way, what a lot of the talk about today, oops, that was the left, oh yeah, there it goes. What a lot of the talk about today is not whether it's a waste or not, it's how to make it a better resource and how to make it more efficiently. And just the background to this picture here, you can see some piles of red mud waiting at a mine site to be applied to treat, in the use of treating a tailings dam where the dam was within centimetres of overflowing. The Dam Safety Committee said the level of water must be lowered, otherwise the dam's at risk of total failure. And the Environmental Protection Authority said if you discharge 1 litre, we'll prosecute you. What do you do? Well, the answer was red mud. And we treated the water from, and I'll show you some figures shortly, being a pretty terrible condition to something that was close to 1,000 times better than drinking water. Okay, what we've got to do first of all is to get this stuff in a safe way to store it. So there are major problems with storing red mud in the current way. It's obviously very expensive to construct and maintain containment facilities. And of course the land that is being used isn't available for any other purpose, and that's also becoming an increasing cost. The caustic red mud represents a threat to any animals or indeed humans that come in contact with it. Last time I was up at Nabalco, I saw a rather angry buffalo that had back-ended, slipped into a drain coming from the red mud dam. There's other problems with there's a risk of the caustic leachate escaping into the groundwater system. And if it does, it's extremely difficult and expensive to rectify the damage. And indeed, the treatment may have to continue long after the discharge of red mud has ceased. And of course, in these days, we're becoming increasingly aware of the costs of public liability insurance and environmental protection insurance and insurance to keep directors out of jail and all sorts of other things. So, as I see it, the best way to reduce this cost is by not having to store the red mud at all. If you haven't got it, you can't get in trouble for having it. And what this means, essentially, is that you've got to find a way of reusing it. And people have looked at this for quite a number of years. But as I see it, the bottom line is really that if you're going to have large-scale reuse operations, you have to find a way of neutralising the red mud. Because the other possible uses don't use enough to make it interesting. So there's several ways we can neutralise it. We can neutralise it by adding acids, waste sulfuric acid and water, acid water obtained from scrubbers. That's one possible way. We can also add seawater, or better still, evaporatively concentrated seawater, or calcium and magnesium rich brines, or even soluble calcium and magnesium salts, or in fact any combination of them. And this is the one I'll focus on much more this morning. Another way of doing it is to use the caustic red mud as a suspension and to spray it into stacks that are emitting potentially acid-forming gases, a bit like the Sumitomo process used at Uralumina, which works extremely well. And of course there's other alternatives such as using gypsum, which for various chemical reasons is not highly effective and it can be quite costly. And there's also using carbon dioxide, which may well consume some greenhouse gases, but again is not, as I see it, a very cost-effective method. And recent work at Alcoa may change my mind on that, but I'm yet to be convinced. Okay, so we'll look at some of these strategies. They could all be used effectively, but the problem is, with the exception of reuse to recover things like titanium, which is still being considered as a possibility for some refineries, we're not going to use very much of it except for neutralizing acid and trapping a wide range of trace metals and other inorganic substances. And unfortunately these requirements mean that there are limitations on what neutralization method you can use. And so we'll just look quickly at some of these. Adding acids is reasonably cheap if you've got sufficient waste acid available and you really like to dispose of it. But the problem is that sufficient quantities are not usually available near alumina refineries to neutralize all the red mud. And the other, in my mind, more serious problem is that if you've spent your red mud neutralizing waste acid like that, then it's no longer available to be used to treat acid mine drainage problems, acid sulfate soils, sulfidic tailings, and the list goes on. So unless some reuse or some new reuse is found, if you're going to neutralize it by adding acid, essentially it means you're going to have to store the neutralized stuff anyway. So the next option is to add seawater or various other types of calcium and magnesium rich brines in various combinations. Now this can be very effective for refineries near the sea, and I guess QAL is the best example of this. They've done an excellent job with it for quite a long time. Now we can also do it, and not all refineries are near the sea, we can also do it with calcium and magnesium rich groundwater brines. And the harder they are, the better they work. And in fact, the whole treatment is going to be a water softening process. And of course, one of the benefits of all this is that it helps conserve fresh water. And if you do a little bit of really cunning chemistry, you may be able to retrieve some commercially marketable salts from the whole process, minerals such as thenodite, mirabolite, and so on. Which may well pay the cost of neutralizing the red mud in the long run, and there's a few procedures being described for this in the literature recently. But the bottom line for any of these techniques is that if you're going to use seawater, you need fairly large volumes of it. For most refineries you need generally about 12 to 18 times the volume of red mud slurry. And this can be a bit of a problem, which I'll come back to. However, the big advantage is that the neutralized red mud that you produce is safe to store indefinitely, and it's eminently suitable for reuse in a wide range of applications. I should point out that in a lot of the work we're doing, we don't call this stuff neutralized red mud anymore. Red mud is not a very sexy name with the public. We like to call it bauxite, which we've trademarked as a name that hopefully is a little more catchy. Okay, so another option is using the red mud fine slurries as a scrubber, as in the Sumitomo process, and this is very effective. It does an excellent job, and it reduces a lot of the classic alumina refinery smells too, in my experience. But the problem is that once you've used it for that purpose, it's lost a lot of its alkalinity and it's not suitable for many other applications. However, if your prime purpose is to clean the flue gases, then it will do an excellent job. But it will need to be stored and ultimately rehabilitated. Okay, so if we neutralise the material, as I said, we call this stuff bauxite now, the neutralised version. What's in it? Well, there's a range of major minerals. We've got all things like hematite, boehmite, gibbsite, sodalite, quartz, cancrinite. They're all pretty innocuous components, although because many of them are extremely fine-grained, they have some very useful properties. But the ones that are of particular interest to us are some of these other minerals. Brucite, for example, magnesium hydroxide. It's a white powder. It actually occurs naturally as a mineral. It's got excellent acid neutralizing capacity, but it's not itself very basic. If you dissolve it up in water, you have a pH of about 7.8. Same sort of things go for things like hydrocolumite and hydrotalcite. And for any of you who have problems with stomach acid and you take Mylanta or some similar substance, this is what you're swallowing. So they're really quite innocuous materials and indeed quite beneficial.